This is SpaceTime Series 26, Episode 130, for broadcast on the 30th of October 2023. Coming up on SpaceTime, the most distant fast radio burst ever seen. A new study shows the moon's 40 million years older than previously thought. And NASA's Mars Curiosity rover finds more evidence of ancient rivers on the red planet, a key signal for life. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have identified the most distant fast radio burst ever detected. The ephemeral cosmic blast, which has been catalogued as FRB 2022-0610A, occurred some 8 billion light-years away. The immense blast, reported in the journal Science, released as much energy in a millisecond as our Sun generates in 30 years. The discovery was made by ASCAP, the Australian Square Kilometre Array Pathfinder Radio Telescope, a collection of 36 12-metre parabolic dishes spread across the Western Australian outback. The study's co-lead author, Stuart from Macquarie University, says the event smashed the team's previous distance record by 50%. Its source was eventually pinned down by the European Southern Observatory's Very Large Telescope to a small group of merging galaxies. Fast radio bursts occur at very specific wavelengths and usually at cosmic distances in the spiral arms of galaxies, usually billions of light-years away. The first was discovered in 2007 in data from the Parkes Radio Telescope in the central west of New South Wales. Since then, hundreds more have been detected. In fact, we now know that these short ultra-bright flashes of radio energy happen all over the sky hundreds of times a day. Some flashes last just milliseconds, but others well over a second, and they can span a wide range of radioluminosities. The very first bursts detected were all singular events, occurring once at a specific location, but then never again. That suggests they were being caused by some sort of cataclysmic event, such as a supernova explosion, marking the death of a giant star. But astronomers are now detecting many fast radio bursts that are repeating from the same location, and that suggests a very different origin. The lead contender is a highly magnetized neutron star called a magnetar. But things like feeding black holes and glitching neutron stars have not yet been ruled out. Now, if there are actually two different kinds of fast radio bursts, it means there could be two separate causes for these mysterious deep space blasts, or it could simply be that all fast radio bursts are repeaters, but with some a lot more active than others. This new discovery also confirms that fast radio bursts can be used to measure the missing matter between galaxies, thereby providing a new way to weigh the universe. Current methods of estimating the mass of the universe are giving conflicting answers, and they're challenging the standard model of cosmology. But if we count up all the normal matter in the universe, all the atoms that we are made out of, and planets and stars and dogs, cats, horses and cars, then we find more than half of what should be there is still missing, and that doesn't even include dark matter. The authors think that this missing matter is composed of ionized hydrogen gas, hiding deep within galaxies and in the space between galaxies, the long, sinuous filaments which connect galaxies to nodes and supernodes, which make up the cosmic web-like structure of the universe. The problem is, if hydrogen gas is hot and diffuse, then it's impossible to see using normal techniques. And that's where fast radio bursts come in, because they can sense ionized material. See, even in space that's very nearly perfectly empty, fast radio bursts can still detect electrons. And if there are free-floating electrons, then there should be an equal number of free-floating protons. The new discoveries represent the limits of what's achievable with telescopes today, although astronomers will soon have some new tools to help them detect even older and more distant bursts in order to even better pin down their source galaxies and measure the universe's missing matter. The International Square Kilometre Array Observatory is currently building two massive radio telescope arrays, one in South Africa and the other in Australia. It'll be the world's biggest radio telescope and capable of finding thousands of fast radio bursts, including very distant ones that can't be detected with current facilities. And the next generation of large optical telescopes, the European Southern Observatory's extremely large telescope, the ELT, a 39-metre telescope currently under construction in Chile's Atacama Desert, will be one of the few optical telescopes capable of studying the source galaxies of fast radio bursts even further away than FRB 2022-0610A. Still, for now, Stuart Ryder says this current discovery has rewritten the textbooks.
So this is a project that Australia is really at the cutting edge of, and that is using groundbreaking telescopes such as the Australian Square Kilometre Array Pathfinder telescope that's operated by CSIRO in the West Australian desert. And one of the great things that this telescope can do that very few others can is to not just be sensitive to these fast radio bursts, which come from all around several thousand per day, but if you're not looking in the right place at the right time and you don't have a wide field of view like ASCAP, you'll probably miss most of them. But having tracked one, the secret to knowing more about them is to be able to pinpoint exactly where they came from. And that's something that currently only ASCAP and one or two other facilities around the world are capable of doing.
Now, one of the important reasons for that is because at this stage there could be two different types of fast radio bursts, single event ones and repeaters. And we're not sure if the single event ones are just really slow repeaters or whether they are just one-off things. And if that's the case, it could mean two separate sources for them. So there are a lot of mysteries associated with the FRBs.
Well, there certainly are, Stuart, yes. And indeed, this particular one that we've just found or just published, as far as we know, it hasn't emitted any repeat bursts, certainly in the 12 months or so that we've been looking at that patch of sky. But we can't stare at that one patch of sky all the time, hoping to see another repeat burst. But at the moment, it does seem like a small fraction, maybe 5% or less of fast radio bursts are seen to repeat at some point in the following few years. And so it's raised the possibility that, in fact, there may be more than one way to form a fast radio burst or the objects that give rise to them. But at the moment, we're still just very much in the classification phase and trying to work out whether, in fact, maybe all fast radio bursts will repeat if we could watch them often enough and for long enough.
How do you produce 30 years worth of sun-type energy in a nanosecond?
Yeah, that's a good question. Well, one of the things, the secrets to that is, given how short these bursts are, typically they're no more than a few thousandths of a second in duration. That really limits the physical scale of whatever object that gives rise to them, in the sense if you had an object the size of the sun, it couldn't put out a single pulse of emission that strong in such a short amount of time because of its physical size. So we know that whatever emits these bursts can only be a few tens of kilometres across. And so that's really bizarre, because there are very few objects that are even that small. So that's why the current most popular theory for what causes fast radio bursts like this one is that they come from the surfaces or somewhere around the outer parts of neutron stars, which are extremely dense states of matter. They are the leftover core from a supernova explosion. But in particular, if the star that exploded and then collapsed had a very strong magnetic field, that magnetic field will get amplified when the neutron star shrinks down. And so it's possible that eventually, when the magnetic field on these neutron stars gets tangled and then has to rearrange, a bit like they do on our own sun, but on a much, much weaker scale. But when that magnetic reconnection happens, you could get potentially a lot of energy released in a very short space of time over a very, very small scale. So that's the best working theory that we have, but we haven't really been able to get close enough into any of these objects to really ascertain if it was definitely a magnetar or not.
What you guys did after discovering the initial burst, you plotted the VLT at that location. What did you see?
Yeah, so once we'd finally narrowed down the position of this particular fast radio burst to the sort of 1 arc-second accuracy, so that's something like 1/2000th the size of the full moon. And at that point, we then transmitted those coordinates to our colleagues at the European Southern Observatory, who operate the world's most powerful suite of telescopes in Chile. They have a set of 4 telescopes, each of which has an 8-metre mirror. We call that the very large telescope. And we had already arranged or requested and been granted permission to use those telescopes to do 2 things. First of all, to use one of the telescopes to take an image of the field where the burst happened, because we weren't sure if there was a galaxy there or not. Thankfully, when the data came back, the images were processed, and we actually saw, funnily enough, not one, but perhaps 3 galaxies, any one of which could have given rise to that particular burst. But we then followed that up with at another of the telescopes, in which we used it to take what's called a spectrum, and we spread the light out from actually those 3 separate galaxies. And it turned out that they all had the what we call the redshift. Their light had been stretched by the expansion of the universe, but it had all been stretched by a factor of 2 in all 3 cases. And so that told us that not only were these 3 galaxies close together, apparently on the plane of the sky, but in fact they all had to be at pretty similar distance. And so for that reason, we think they're almost certainly a group of galaxies that are so close together, they're probably in the process of gravitationally interacting with each other, possibly even given enough time, they will come together and merge into one single galaxy. But for now, we believe this is definitely the host system where this fast radio burst came from. And from that redshift that we measured, that tells us that the light that we see coming from those galaxies, and indeed the radio pulse that we saw as a fast radio burst, had to have been traveling for almost 8 billion years to reach us here on Earth. That's just mind-boggling. I mean, that's twice the age, almost twice the age of our own sun.
When you look at something like these galaxies, can you actually tell what they are, whether they're elliptical or spiral or irregular or whatever?
Sometimes, yes, if they are close enough and we take nice deep images with these the very large telescope in Chile. If you're lucky, you might be able to make out what is fairly clear spiral arm structure in a few of the more nearby cases. But as they get further and further away, our ability to see that level of detail from the best ground-based telescopes diminishes. In a few cases, we've used the Hubble Space Telescope instead to take images which can be even sharper. But even at the distance of this most distant fast radio burst, the Hubble Space Telescope images that we've just obtained of that system don't yet show any clear spiral arm structures or even what we call tidal tails or other evidence that these galaxies are definitely undergoing a merger. But given how far away these objects are and just how faint that structure would be, it's not really a surprise that we can't yet tell whether the particular galaxies in this system are spiral galaxies like our own Milky Way, or indeed whether they are older galaxies who stopped forming stars quite some time ago.
Is knowing sort of what the galaxy looks like and knowing from what part of the galaxy the fast radio burst emerged, that would help you narrow down the sort of likely sources. If it's an area full of lots of young stars, then that's where you're going to find big stars that are going through their life cycles really quickly and are likely to become neutron stars and magnetars.
Exactly. Yep. And so that's certainly a scenario that we have seen already in a few of the more nearby fast radio bursts. We have been able to match up their locations to the spiral arm regions, very close to where stars are likely to have been formed recently. In this particular case, though, as I say, the galaxies involved are just too far away for us to be able to make out that level of detail. But it is interesting, though, that whenever we've seen galaxies closer to us that are undergoing this type of mergers or interactions, inevitably there'll be an elevation in the amount of star formation that is happening as the gas clouds in these galaxies get smashed together. Inevitably, some of them will begin to form stars. We'll get more stars being formed, and as a result, ultimately, there'll be more supernova explosions, and that is more likely to lead to magnetar objects, which we believe are the most likely point of origin for these fast radio bursts. So it all kind of fits that scenario, but we just don't have the smoking gun that we would want to say, yes, it was definitely a magnetar.
Now, another thing you've been able to do with this observation is help work out what's happened to all the missing normal baryonic matter in the universe. This has been one of the big questions. We're not talking about dark matter here. We're talking about the atoms and stuff that you and I are made out of. These observations of fast radio bursts is helping with that as well.
Yeah, so one of the really remarkable things about fast radio bursts is that they carry with them an imprint, if you like, of all of the free electrons that they pass on their way from the galaxy where they occurred to us here on Earth. And what that does is actually slows down the signal arriving at lower frequencies, and so that arrives later. And the more of these free electrons it encounters, the more that signal gets stretched out to lower and lower frequencies and later and later arrival times. So already from when we first detected this particular burst, because it was so stretched out, we surmised that it probably had come from a great distance, perhaps the most distant fast radio burst ever. But it turns out there's more than one way to encounter free electrons. Sometimes it's all the stuff between galaxies, and sometimes it might be much more local to the burst. So to be absolutely sure, that's why we had to go to the telescope, the very large telescope, and get a measurement for the distance of the host galaxy independent of the electron density that the fast radio burst passed through. And that was really the key finding that, yes, this definitely was the most distant and oldest burst burst that we'd ever found. Given that pulse that we saw, as I say, it enables us to measure all of those free electrons. Those free electrons had to come from atoms, and so for every electron that we detect, that means there's many more atoms out there. And we think that these atoms, the reason why they have free electrons is that they're very, very hot, and that electrons are then free to wander away from the atom that they would normally be circling around. And because this gas is so hot, but very, very thinly spread out, there's just no way that we've been able to detect it at any other wavelength until now. So fast radio bursts have been key to reassuring us that what we have referred to as missing matter, because when we tried to look for it, we couldn't see it. But really, it actually should have been called unseen matter. But now, thanks to fast radio bursts, all of that missing matter has been found, and all is right with the universe.
And that missing matter is most likely ionized hydrogen, I take it, that is either inside some galaxies or in the intergalactic space between the galaxies, along the filaments that make up the cosmic web of the universe.
Yes, that's right. We believe it's what constitutes that cosmic web, as you say, the filaments where the gas tends to cluster because of gravity, but that would then surround the large, effectively voids or relatively empty regions. So whenever we look at the fast radio bursts coming from different directions, we notice that the average density of this material fluctuates quite a bit, and that gives us confidence that although we don't know quite where those bursts, where that material is distributed along our line of sight, but given how much it can fluctuate even over a small patch of sky, suggests that the stuff between the galaxies is actually quite lumpy in its distribution. And again, this is the kind of pattern that was predicted from the Big Bang model for the beginning of our universe. So it's nice that from a totally different phenomena, fast radio bursts, whose origin we don't still completely understand, but already it is telling or confirming for us pretty fundamental things about our universe.
That's astronomer Stuart Ryder from Macquarie University. And this is SpaceTime. Still to come, a new study of ancient lunar rocks shows that the moon's actually 40 million years older than we previously thought. And a new analysis of data from NASA's Mars Curiosity rover suggests that many of the craters in Mars today could once have hosted lots of flowing rivers. And where there's flowing water, habitability is always a possibility. All that and more still to come on SpaceTime. A new study of lunar rocks brought back by the Apollo 17 mission showed that the moon is actually some 40 million years older than previously thought. The findings, reported in the journal Geochemical Perspectives Letters, suggest that the moon must have accreted from ejection debris some 4.46 billion years ago, 40 million years earlier than the 4.425 billion years previously thought. To reach their conclusions, scientists used the Northwestern University's atom probe tomography facility, which was able to nail down the exact age of the oldest zircon crystals found in samples brought back by astronauts in 1972. The study's lead author, Philip Heck from the Field Museum in Chicago, says radiometric dating works a little bit like an hourglass. In an hourglass, sand flows from one glass bulb down into the other, with the passage of time indicated by the accumulation of more and more sand in the lower bulb. Radiometric dating works in a similar way, by counting the number of parent atoms and the number of daughter atoms they've transformed into. The passage of time can then be calculated because the transformation rate, that is the half-life of the element, is well known. According to the giant impact theory, a Mars-sized planet, which astronomers have called Theia, collided with the early proto-Earth some 4.5 billion years ago, melding the two bodies together into a massive molten magma ocean, which eventually differentiated and cooled, forming the present-day Earth. Ejecta from that impact was flung into space. This eventually coalesced and accreted to form the Moon. Initially, like the Earth, the lunar surface was also molten, and as it cooled, zircon crystals began to form. The atom-by-atom analysis using atom probe tomography allowed the study's authors to count how many atoms in the zircon crystals have undergone radioactive decay. See, when an atom undergoes radioactive decay, it sheds a proton and neutrons, transforming into different elements. Uranium, for example, loses protons and neutrons, decays into lead. And because we know the rate at which uranium decays into lead, we can work out when that zircon crystal was formed. Heck says it's important to know when the moon formed because the moon plays an important role in our planetary systems. It stabilizes the Earth's rotational axis. It's the reason there are 24 hours in the day and the reason we have tides. In fact, without the moon, life on Earth would look very different. This is SpaceTime. Still to come, the Curiosity rover finds new evidence suggesting Mars was once a planet loaded with rivers. And later in the science report, a new study warns that the world is now heading towards 6 global tipping points, beyond which the planet's systems will no longer be able to cope. All that and more still to come on SpaceTime. A new analysis of data from NASA's Mars Curiosity rover suggests that many of the craters on the red planet today could once have hosted habitable rivers. The findings, reported in the journal Geophysical Research Letters, are based on numerical models which simulate erosion on Mars over millennia. The study is the first to map erosion of ancient Martian soils by training a computer model on a combination of different satellite data, Curiosity images, and three-dimensional scans of the stratigraphy, that is, the layers of rock or strata deposited over millions of years beneath the Gulf of Mexico seafloor. The analysis provided a new interpretation for common Martian crater formations, which until now had never before been associated with eroded river deposits. The authors found that common formations inside craters, called bench and nose landforms, are in fact most likely remnants of ancient riverbeds. The study's lead author, Benjamin Cardenas from Penn State, says scientists are finding evidence that Mars was likely a planet of rivers. He says the data is showing signs of this all over the red planet. Prior studies of satellite data from Mars had already identified erosional landforms called fluvial ridges as being possible candidates for ancient river deposits. Using data collected by the Curiosity rover inside Gale Crater in the Martian Northern Hemisphere, the authors found signs of river deposits that are not associated with fluvial ridges, but rather bench and nose landforms that have never been linked to ancient river deposits before. Cardenas says this suggests there could be undiscovered river deposits elsewhere on the red planet, and that an even larger section of the Martian sedimentary record could have been built up by rivers during a habitable period in Martian history. On Earth, river corridors are important for life, for chemical cycles, for nutrient cycles, and of course for sedimentary cycles. And everything is now pointing to these rivers behaving in a similar way on Mars. Cardenas says the research indicates that Mars could have had far more rivers than previously believed. And that certainly paints a more optimistic view of ancient life on Mars if it ever existed there. In fact, he says it offers a new vision of Mars, one in which most of the planet once had the right conditions for life to exist. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. A new United Nations report is warning that the world is now heading towards 6 global warming tipping points, past which the planet's systems will no longer be able to cope, resulting in the risk of catastrophic impacts or collapse. The 6 interconnected risk tipping points are accelerating extinctions, groundwater depletion, mountain glacier melting, space debris, unbearable heat, and an uninsurable future. The report points out that here in Australia alone, approximately 520,940 homes are now predicted to be uninsurable by 2030, primarily due to increasing flood risk, leaving people without an economic safety net if and when disaster strikes. And that's opening the door to cascading socioeconomic impacts in high-risk areas. The authors say that once these tipping points are crossed, it'll be difficult to go back. Well, it's a question we've often asked ourselves. Now, a new study is looking at why people like fatty foods so much, and it suggests it may be the texture. The findings, reported in the journal Neurosci, looked at volunteers' brains while they sampled and placed monetary bids on liquid foods with different levels of fat and sugar. They found a brain region called the orbitofrontal cortex was responsive to oily smooth textures produced by fatty liquids on the surface of the mouth. The authors found that people with orbital frontal cortexes that were more sensitive to texture seemed to eat more fat and to offer more money for the fatty foods. The authors say this brain region responding to smooth textures might be guiding your eating behaviour. They say that future research could look at redesigning foods that seem fatty through texture but are tricking our brains into preferring healthier, lower-fat foods. At a time when marine life is disappearing from the world's oceans, researchers are celebrating the discovery of a new species of coral reef fish in the southern waters of the Great Barrier Reef. Named the Lady Elliot shrimp goby, the previously unknown fish was found as part of a University of the Sunshine Coast-led project that's been mapping the changing biodiversity on and around Lady Elliot Island, a tiny coral cay at the southern end of the Great Barrier Reef. You can read all about the tiny fish and its discovery in the Journal of the Ocean Science Foundation. Scientists have discovered a casual link between spiritual people and a decision not to take vaccines. Sociologists researching the role of religion in vaccine attitudes and behaviours found that with all else being equal, people with the lowest belief in some sort of intervening higher power tended to be vaccinated at least 88% of the time. In contrast, those with the highest belief in an intervening higher power were found to have been vaccinated only 73% of the time. Tim Mendham from Australian Skeptics says the findings show that both religious people and New Age hippie types seem to have lower vaccination rates.
What they found, what studies have found out, was that in 3 years after the start of the COVID pandemic, about 1 in 5 Americans still hadn't received a single dose of any COVID vaccine. And they're trying to find the reason for that. That's a big number, right? That's seeing as Australia, you're getting up towards 95% of the first vaccine, which is about what you want.
That's herd immunity.
Numbers for herd immunity. The second and third vaccines probably didn't get the same number. People become complacent and apathetic towards it after a while, which is sad because you keep quoting how many people are dying of it and still are.
Yeah.
But about 1 in 5 Americans have not even had one dose. They're trying to find out why. So there have been studies of religion and religious beliefs about their attitude towards conspiracy theories and especially vaccines and COVID vaccines. And what they found out in the studies, they were looking at their religious beliefs and then threw in questions about various scientific things. They found out that those who see the Bible as either the inspired or the actual Word of God were less likely to see vaccines in general and the COVID vaccine in particular as safe and effective. And the reason is largely because God will look after you, right? And therefore doing something, you don't need to do it, in other words. God will look after it. You don't need a vaccine, no matter whether you believe it or not, you don't need to. And then there are other people who, on the sort of other side of the coin, who are, you might call spiritual people, who believe in new age things, nature, sort of spirits and that sort of stuff, who would say vaccines aren't natural, so I won't use it because it's dangerous.
Licking the back of a frog is? I don't understand that.
Yeah, I know. The back of a... But yeah, this is your typical hippie sort of mentality that says that I won't take a vaccine because it's not natural, and the religious group, the standard religious group will say, I won't take the vaccine because God's going to look after me anyway, so why take something extra? And what they found out was that these sort of attitudes extend into conspiracy theories and all sorts of areas. Therefore, what they're saying is that there's a link between religious belief or spiritual belief and low vaccine rates. And certainly the low vaccine rates is being well established in Australia because you get areas of high hippie populations which have a low vaccine rate. But there's also this issue of religious people, and I think America would be stronger than it is in Australia, perhaps certainly Europe. It's less strong there, but it still exists, and it's growing as well.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from SpaceTimeWithStuartGary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.